Okay, the next method we're going to look at today is the simplified Bishop's method, sometimes called Bishop's simplified procedure. There is a more sophisticated Bishop's method we'll talk briefly about at the end of this section. But here goes. The simplified Bishop's method, the key simplifying assumption is that the side forces are horizontal, meaning that the vertical side force components are equal to 0. Or that they cancel, and that reduces our number of unknowns. So if we sum forces in the vertical direction, so this is, excuse me, I'm going the wrong way. So we're going to sum forces in the vertical direction. So we have W, S, and N. So we have W is acting in opposite direction of the N times the cosine of alpha, and S times the sine of alpha. So N cosine alpha plus S sine alpha minus W is equal to 0. And the side force S is equal to the shear stress times the width of along the base of the slice, and the shear force, or excuse me, the shear stress is equal to the shear strength, the mobilized shear strength, the shear strength divided by the factor of safety, and which is, if we then put that back into this equation, excuse me, if we look at the mobilized shear strength along the bottom, we get C prime delta L plus N minus U delta L. So this is the normal force minus the pore pressure force times the tangent of phi prime. And if you substitute this value for S up into here, you get this equation shown at the bottom. And then if you solve that for N, you get this equation for the normal force, and you'll notice that it has the factor of safety in the denominator and in the numerator. So because of the representation of the mobilized shear strength. And so the effective stress is equal to the N over delta L, the total stress minus U. And then if we go back to our general equation, which we saw just a minute ago, when we're talking about ordinary method of slices, this is the equation based on moment equilibrium around the center of the circle. We have the sum of the forces on the bottom of the slice, resisting failure, and then on the denominator we have the forces driving failure. And this is, again, derived from moment equilibrium, where the radius term has been factored out. And so if we plug this equation for sigma prime in here, and this equation for N into here, combine those three previous equations, and then solve for F, we get this equation shown on the top. And you will notice that it has F over here and then F on the left. So basically you have to assume a value for the factor of safety F and then solve for F, and then repeat until those two match. So it has to be solved iteratively. If we do a total stress analysis, we're using total stresses and total forces instead of effective stresses. It simplifies to this form shown on the bottom. Still has F on both sides. And then if phi is equal to 0, then it simplifies to this, which should look familiar. It's what we saw with ordinary method of slices, Swedish method, etc., for the phi equals 0 case. So once the factor of safety is found, we can go back to the equation we derived for the normal force and calculate that. And if you compare this to the normal force for the ordinary method of slices, you can see the difference. And that's the primary difference in the solution is due to the differences in the normal force. Both use the same overall equation. Again, this is our equation for the moments about the center of a circle. And so, in summary, the simplified Bishop's method, we have our unknowns are the n normal forces along the base of the slice. The one factor of safety gives it n plus 1. We solve n equations for vertical force equilibrium and one equation for overall moment equilibrium, so we get n plus 1 equations solved. And so again, since it's based on moment equilibrium from a circle, you can only use it with circular slip surfaces. You can't use it with non-circular surfaces. The simplifying assumption was that the shear forces on the sides are 0, so the resultant force on the side is just horizontal side force. We satisfy overall moment equilibrium and then force equilibrium on each slice. It's more accurate than the ordinary method of slices, especially for cases where you have effective stress analysis and high pore pressures, where the ordinary method of slices can get you into trouble with its unconservative answers. And finally, there is, in fact, a Bishop's complete equilibrium procedure. Of course, in this case, we do not assume that the shear forces on the side sum to 0, but we make an assumption about the vertical side forces and check for equilibrium, and then you iterate with both the factor of safety and the side forces until you satisfy equilibrium. It's fairly time-consuming and complicated. There are simpler complete equilibrium procedures, which we'll talk about. Therefore, you don't use this a lot, but the Bishop simplified method is used quite a bit.